Imagine you have an apple. Imagine you have an apple. And if you have only one apple, then you have only one apple. Good morning, fellow mathematicians! Welcome back to another video. No, you're not mistaken, we are going to deal with this piece of garbage today. If you also think this is easy AF, then post #trivial down in the comments. I'm also going to post #trivial down in the comments and into the video description because this is really quite easy, but it has been requested, so we are going to give it a shot. I'm going to do it 3 little ways today. The first 2 are going to make use of the standard approaches you are going to learn in your Calc 2 class probably, for example, I don't know. And the last one is going to be kind of the visual way. So let's go ahead and get started. I would like to do integration by parts on here. So we need something to differentiate, something to integrate. We have evaluated this one quite often already in other integrals. It pops up all the time. So we don't really know how to integrate the natural log of x, so why not differentiate the natural log of x, leaving us with 1 over x in the process. But what to integrate? Well, imagine you have an apple. Imagine you have an apple, and if you have only one apple, then you have only one apple. So I hope this makes sense. So natural log of x is the same thing as 1 times natural log of x. So we are going to integrate 1. This was the worst thing I've ever done on this channel. That was so stupid. That's when I do private tutoring, I always do something with apples or real life applications because children don't know how to do shit in mathematics most of the time, and then I say, well, what happens if you add nothing to something? So you have one apple and you don't lay another apple next to it. What are you going to get? Well, still one apple, yeah, and the same thing here. So yeah, that's something I do sometimes. If we integrate 1, we are going to get x, okay? So multiplying this together and taking the integral of this thing right here, we are going to get, okay, natural log of x times x from 0 to 1 minus an integral running from 0 to 1 of x over x, which is nothing but 1, dx. Evaluating this is actually quite easy. We are going to get x from 0 to 1. Okay, it's just going to be 1. So at the moment we have, okay, here we have to apply limits. So if we plug 1 into here, this is 1 times the natural log of 1 is going to give us 0. So this first part is going to vanish. And then we are going to have natural log of 0 times 0. Natural log of 0 is going to diverge to negative infinity. So we have to do more work. So limit, and that's written in Arabic letters. So that's also quite funny. People are mocking me all the time because my limit looks like I'm writing Arabian letters. So that's quite funny actually. Allahu Akbar, I would say, here on this limit. So limit. And we have the second part of the integration, so negative. Limit as x approaches 0 of the natural log of x times x. And here we just have -1. Okay, so this is a negative infinity times 0 situation. So why not turn this x into 1 over x to get this right here. Now we can actually use Papa L'Hopital, meaning we differentiate this numerator with respect to x and this denominator, leaving us with, okay, -1 stays as it is. Then we have negative. I'm going to refer to this limit as capital L, and then differentiating natural log of x leaves us with 1 over x. And differentiating 1 over x gives us -1 over x squared, because 1 over x is nothing but x to the -1. So -1 over x squared. Overall, this is -1. Okay, this doesn't look any good at the moment, but we're going to turn those complex fractions around, taking the reciprocal here. Okay, negative becomes positive. The limit of, okay, putting this in the numerator over x, we're going to get rid of this. Let x approach 0, it's going to give us 0 on this part. So -1. So this thing right here, this improper integral, actually has a finite surface area, you could say, under the curve. Even though our natural log looks something like this right here. It's a finite area we have down here. And with this technique, you could say you can actually construct, for example, Gabriel's horn, if you don't know what it is. So that's basically a surface with infinite length, you could say, infinitely stretched, but with finite surface area. Yeah, so that's quite cool. This has been the first method, and now off to the next one. Like I said, we're going to evaluate it using the standard methods of integration you basically learn in your anal or calculus class. We did integration by parts, now we are going to do substitution. And why not let natural log of x be equal to t, for example. Okay, then we differentiate both sides with respect to t in this case. We're going to get the differentials. Okay, this differentiated is nothing but 1 over x dx. Now it's our turn to find out what 1 over x actually is. To substitute everything with respect to t. Okay, what we can basically do, we can multiply both sides by -1 is not equal to 0 on here. Okay, then we get negative t being equal to negative natural log of x. Using the natural log property, we can bring this negative sign to the inside as a -1 power. X to the -1 power is nothing but 1 over x. Meaning we can apply the base e on both sides to get that e to the negative t is equal to, well, 1 over x, since e to the natural log of 1 over x is going to cancel out to just 1 over x. We can plug this chunk into here and get that dt. It's nothing but e to the negative t dx. Multiplying both sides by e to the t, it's going to leave us with this chunk right here. And e to the t is not equal to 0, that's why we can multiply both sides by it. Well, basically we can plug everything into here now. We are going to get an integral running from, now we have to plug 0 and 1 into our original x into here. Okay, this has been our original expression. If we plug 0 into here, natural log is going to diverge to negative infinity. So negative infinity is our lower bound. If we plug 1 into here, natural log of 1 is just 0. Coolio, we've done that. T is nothing but natural log of x. dx is nothing but e to the t dt. Now we can once again make use of integration by parts. This time we would like to differentiate t because it goes to 0 way faster. Okay, then it goes to 1. I'm going to just do one iteration. You're going to see why I'm doing this. We're going to integrate e to the t because this integrated is just e to the t once again. Multiplying this together, taking the integral of this right here, it's going to leave us with t times e to the t from negative infinity to 0 minus integral of e to the t dt from negative infinity to 0. Okay, now we have this chunk right here. If we plug 0 into here, this is going to vanish. Then we have negative the limit as t approaches negative infinity of t times e to the t. The thing here is e to the t is going to grow way faster than t. You can once again make use of L'Hopital's rule to turn this into t over e to the negative t, you could say. So that's something you can do. Overall, this thing right here, since e to the t is going to grow way faster, it's going to go to 0 in the end, leaving us with negative this chunk right here. You can simply evaluate this and you are going to get -1. We already know what this is going to evaluate to. So integrating e to t is really quite easy. You know how you can do this. And here comes our third way in. So this has been the second way. It's really quite easy, but I've only derived this to show you a little interpretation visually, you could say. So what you can also do is turn this chunk right here with another substitution. So for example, let u be equal to negative t or t be equal to negative u. That means that dt is nothing but negative du. And you are going to get something equivalent, namely the integral from 0 to 1, infinity, the negative integral from 0 to infinity of e to the negative u du. Okay, this is something you get right here. we can take a look at this visually a little bit. So no matter what you do, this right here is our natural log of x. It has this area right here. But what we can do, we can place a little mirror on here, right, on this diagonal, to get this function right here. So you see, this has been this function right here, with this area under this curve. But if we take this in a negative sense, so in a normal case we have this chunk right here, so this function from negative infinity to 0 is this area, but if we take this area negative, we are going to get exactly this area under this curve. So by placing a mirror on here and just changing the sign of this area from positive 1 to negative 1, we are actually going to get the desired area right here. So this is a visual approach to this whole thing. And yeah, this is basically it. You can just simply evaluate this right here. It's going to make perfect sense. Anyways, yeah, this is basically it. I thank you guys for watching. If you did enjoy this video, please like and subscribe and recommend channel if you like. This was just a chill little video regarding this little improper integral. Tell me in the comments which was your favorite way. So I really don't like visual approaches, but most people seem to like this garbage right here. So I might as well put it in my videos a little bit. You can support channel by buying those t-shirts I created, or support channel on Patreon, or visit my website or something. And well, up until the next video, I appreciate you guys. Love ya. Have a flammable day. See ya.